Hi, Reg audience. Welcome back. We are live today talking about generative AI. For the moment, I am real, but for how long? Probably not very long. Well, it's been good while it lasted. Well, generative AI is something that you are probably thinking of investing in for all its capabilities. However, it might be a project that's going to be technologically extremely difficult to pull off. So we're going to be helping you to do that, talking about how you can maximize your efficiency. Well, who's going to be doing the talking about that? We welcome back a friend of the Regcast, James Coomer from DDN. Hello, James.
Hello. Thanks for having us.
Well, I'm glad you're here. We don't give you the easy topics ever, but then again, you wouldn't want that, would you? Now, remind everyone, what does DDN do? What do you do there?
So DDN for 20 years has been building storage and data management solutions for the toughest challenges out there, including AI, HPC, and large-scale unstructured data problems. And I am Senior Vice President for Products.
Good. Excellent. Now, today, you are joined by one of your partners in innovation, I suppose we call that. Premal, welcome.
Thanks, Tim.
Now, I guess everyone knows about NVIDIA, but what do you do there?
So, Tim, I am actually the Senior Director of the DGX Systems and Solutions team, and I am helping NVIDIA and the rest of the world bring NVIDIA solutions to the enterprise.
Now, we are live, as I said, so if you've got any questions you want to ask, any points you want to make about this, then you know what to do. Type it into the box, comes through to me. I ask the guys about it. However, they've got quite a lot to tell you, so you're not going to be short of things to think about after the next 30, 40 minutes. We better get on with it. Premal, first of all, there's been a lot of AI hype over the last few months. Well, today we're sort of buying into it, aren't we?
Oh, yes, we are. There has been a lot of it in terms of what ChatGPT has done since the beginning of this year. And it has brought a lot of the AI technology that we've been working for over the last 5 years or so or more to the forefront. For the users and of AI and the Reg audience today, if you don't know, NVIDIA has been doing a lot of work not only on the component side, so not only on the GPU and the accelerated ASICs that we build, but also in terms of the platforms and the software that is required for AI. And I'm just showcasing some of the work that we've been doing over the last 10 years or so in various aspects of and various use cases that we have been bringing to the forefront. Whether it's speech AI, big NLP, recommender systems, or autonomous vehicles, or telecom, or cybersecurity, we are working on end-to-end applications and frameworks. And what you see at the bottom out there, which is around Riva, Nemo, Merlin, these are some of those frameworks that we are making available so our enterprise customers can easily consume them without having to start from scratch. And the idea being that with any of the underlying accelerated platforms that NVIDIA provides, we kind of continue to innovate and make it easier for our customers to consume these new frameworks as they are getting developed and implemented on the newer accelerators that we develop.
Because one thing about this, sorry, Prabha, one thing about this is it's not just a sort of an evolution of what they've been doing before.
Correct. It is just not an evolution of the way AI has been. It's very different. What we have seen is a typical application in the data center is just north-south traffic. But with AI, what has happened is that it has changed the paradigm or the model of the applications going forward. There is the aspect of the data, which is really important as we are building these AI applications. There's the aspect of training, which is completely new to a lot of these technologies that are getting deployed around AI, what you need to do around training and how you use that with the data to actually come up with the final product, which is going to be your inference system, which will then go into production. So when we talk about text to speech or speech to text or anything around autonomous vehicles, what will come up is, hey, I'm going to come up with a training set and then go into is building the end application that then the end user will see. Over the last, I would say is last year, everybody has heard about ChatGPT and what people can do with LLMs. It has come to forefront. It's like the iPhone moment for AI. There has been a lot of work that we've seen happening. And over the last 5 years, you'll see is the number of papers that have gone into LLM and research has just skyrocketed. From Transformers and Bird introduction by Google in 2018 to GPT-3 by OpenAI in 2020, that has just opened the doors in terms of what those capabilities, what people can do with those kind of frameworks, right? And a lot of companies will need to make this infrastructure spend as they move forward and start using these large language models for their environment, for their applications going forward. And here at NVIDIA and with our partners DDN, we are here to help them through that journey. It's not that they have to start from scratch. We at NVIDIA have learned a lot and are making it available to our customers and all the rest of the world so that they can consume this technology as we move forward, right?
Just a quick one. Everyone's very excited about this, but could you just be specific for a moment about why generative AI produces value for businesses, for the sort of people who are watching today?
So if you think of it, the way to think about generative AI is we have a lot of information that's available to us. And these AI frameworks can do, can provide you a lot more information as we go forward in terms of learning from the information that has been collected and then providing you a guidance as a recommendation engine. So if you are going to Amazon or you're going anywhere to do any shopping online, you see a lot of recommendations coming out to you. So what we are seeing is that we are generating based on your use of some of the consumer items that you're purchasing, and we are getting those recommendations based on what you have done in the past or what people in your area might be doing, and that's being made available. In terms of image generation, we can come up with is image generation becoming something that you can ask for, like, hey, I want to see a camel on the moon, and I can generate an image which will be generated by this particular model for you, right? So that's where generative AI is coming in, right? And what we are seeing is that people are getting very creative in terms of how they are using these generative models. And there are different ways to consume this as we move forward. Whether you consume it in the cloud, you can start with that, or you can start building something that would be your foundational model on which you as an enterprise will develop going forward, right? As an example, you can, as a very specific example, you can think of as a chatbot that is very different for a customer service agent for a telco versus something for a bank. So for each of those verticals, you can go and use the data that is specific for that particular model as a foundational capability, and then develop what would be more appropriate with the right guardrails for that particular vertical, right? So that's how you can go developing things with generative AI for different verticals and different focus going forward. Now, consumers can consume this in various ways. As I said, you can consume it in the cloud, you can consume it as APIs, you can consume it or build your own infrastructure with your own foundational models. And at NVIDIA, we have all these various options available to the customers. right? More than that, as part of the DGX team, what I've been doing is been working over the last 6 years at NVIDIA, creating all these different systems and making it easier for enterprises to consume this technology. And a lot of it has to do with is how things have evolved. When we started, it was 1 or 2 GPUs or 8 GPUs at the most where the models were. But now what we are seeing is these models have become far more complex, and the amount of data that they have to go through for developing the final framework or the final application is significantly large. And what we are trying to do as we go forward is to make it much more easier for everybody to just start off from a baseline and then develop spend more time on developing the AI application that they're going to use for their final solution, right? So we have the DGX system that's available. It will give you a full set of performance that we share with our customers. And then we come up with the idea of the SuperPOD. The SuperPOD is basically something large, like large language models like GPT-3 or GPT-4 as we go forward. As they become more and more complex, meaning the complexity comes from the number of parameters that they are using. So as they go into these billions of parameters, the amount of time that it takes to run a particular model to get to a particular outcome becomes significantly harder, right? A 5 billion parameter model today is considered pretty small. It takes roughly 20 DGX A100s about a week to run to get to a particular, I would say, error number or whatever that you are targeting as the outcome that you are pushing for. And as we are seeing the push for 175 billion parameters or 1 trillion parameters, the size of the clusters are getting more and more complex. So not only are we running models on a single GPU, but on multiple GPUs, but also across multiple DGXs. And the DGX SuperPOD is a reference architecture that we have put out there, which makes it easier for customers to see is how NVIDIA does it internally and how our researchers are using this and developing the software that will be used and everybody can build on top of going forward. So we provide the frameworks on a monthly cadence. So customers can either take it as something what we offer as our registry option and download it from there, or use our LLM Nemo frameworks in the cloud directly as an API if they choose to do that, right? And all of this is made available on a monthly basis. So instead of rebuilding the underlying model, what the users start doing is just fine-tuning and getting to the right accuracy that they are targeting for their end outcomes. So that's what the SuperPOD is. We built a fast supercar, and the SuperPOD is a racetrack that you can drive at full speed, making sure that you don't want to worry about the infrastructure itself. Right.
One thing that we know is that certainly in the next 12 months, 24 months, there's going to be a huge amount of development, a huge increase in the number of parameters, for example, going on. If you want to stay competitive on this is the time where you're going to need some investment, I guess.
Absolutely. This is the time as everybody is trying to develop and figure out where they invest in, whether it is building, starting in the cloud or doing something on-prem, and building their own foundational models going forward. And I say foundational because this is an evolution that everybody has and a journey that everybody has to figure out for their own selves as they move forward, right? And this evolution means that, hey, I'm going to learn every iteration of the application that I'm developing and move forward from there. Now, the DGX SuperPOD, the way we have designed and developed it is, you can think of it as I'm making it available as a scalable unit, which is like a building block of 20 or 32, depending upon whether it's a A100 or a H100 GPU that we are using. And all of this comes from the design comes from the fact that we have only so many InfiniBand ports or so many Ethernet ports that are available to us. So how do we make sure that we make it in blocks so that customers can consume it very easily? So depending upon the AI workload that you're targeting, I would say is customers can start off with 20 DGXs or smaller and then scale up from there very easily. We have separate environments or separate networks for compute. I mean, compute is what GPUs talk to other GPUs in the fabric over. The storage fabric is different. And the in-band connectivity is a different fabric connectivity also. And the reason we do this is because we don't want to stop any kind of or impact any kind of work between the GPUs or between the system and the storage environment, because we want to continue to let the application or the framework operate over a long period of time without being interrupted. A lot of these AI applications are very read intensive, but what we are also seeing and what we put in the effort around DGX SuperPOD stack is around checkpointing. So a lot of our frameworks continue to do checkpointing, and that can be very heavy on the storage side. And the reason to checkpoint is that things do happen in the data center. And when you have a workload that's running for weeks at a time, how do you ensure that you can recover from it? And so checkpointing every 4 hours or at certain periods of time is very storage intensive. So we need to make sure that our SuperPOD architecture separates out what we do for compute and storage, and it does not interfere with this environment, and we can restart the work when it's required, right? The DGX SuperPOD, the way we deliver it is through NVIDIA Professional Services. So customers get is, hey, this is the way we set it up at NVIDIA. We build it for you. We ensure that you are getting the exact same performance that we saw in our labs and in our deployments. And we are handing you the keys for this supercar on a racetrack that we know will function the way it is supposed to. And from there, they can start building and evolving around their AI and generative AI applications moving forward. Right? And if you see is some of the things that we do, we publish our reference architectures so that anybody can refer to them. We have it on our website. DDN publishes the same as to how this particular solution can be implemented very quickly. And today, a lot of this is around data center availability and around component availability and timelines around that. So as customers are walking through or planning their AI journey, they should start with some of the information that's available to them from NVIDIA and from DDN regarding how to build these SuperPODs and all the information, whether it's the data center, whether it's the SuperPOD itself or the applications, what they need from us, right? And all of that is available. More than that, I would say there are a couple of more additional slides around what a scalable unit looks like. I'll not go into those details. And if there's more interest on it, I can point your readers to some of this information. And then I just wanted to share one more thing is how NVIDIA does this internally. Every time we come out with a new SuperPOD or a new DGX platform, we at NVIDIA consume it internally. We create our own cluster. We run that cluster at full performance to make sure that the designs that we are proposing for AI and for our customers, they can replicate it easily, and they can see where it stands in the top 500, in the green 500, and how efficient these systems are. The whole idea is to help educate all our customers to make sure that they are following the same recipe, so that it is very easy for them to continue to innovate on top of everything that NVIDIA is providing them as we go forward.
Okay, thank you, Parimal. James, 3 magic words, I guess, the Parimal said in that: very storage intensive generative AI. And this is where you come into this story, isn't it? Because you have to work closely with NVIDIA if we're going to get the performance we need.
Yes, don't we know it? we finished on this picture here. I've got a similar picture on the next slide. We've been working with NVIDIA.
We never used to show these sort of pictures, but it's, you know, it's become so, this is what it is.
Exactly. We got less ethereal after the pandemic.
Yes.
So here we are. Here's a very sort of example system. You can see the DDN storage. I'm going to talk about the data and the storage. And here's the DDN system. I'm housed inside one of these SuperPODs. So yeah, I said, don't we know it? We've been working with NVIDIA now for 3 years on Selene, and they genuinely have been running these very, very large-scale production applications, and of course, coming across data challenges with storage. And then we've been developing essentially fixes or optimizations to those right over that period, very actively, very back and forth, which means the reference architectures you get are really the fruits of real at-scale AI at the very largest scales in very tight combination between ourselves and NVIDIA. So what I want to do, if you don't mind, Tim, is maybe just give people a little flavor about what a parallel file system is, and then talk about a couple of the things we've done to optimize and really maximize its efficiency. And it's really a big efficiency play. People are constrained by data center power. So the best they can get out of that power footprint is really one of the biggest key things we can help customers with.
Right. And the point about this is this is what you've been doing and has been working. It's not, let's have a go with this. It might work.
Yeah, we've rubber stamped this across many, many SuperPODs in the world, the same combination of DDN, NVIDIA, repeat, and perfect as we go along. But yeah, we've deployed this many times.
Yeah, complexity, cost, and risk here. I would have thought that any kind of AI, generative AI deployment at the moment has plenty of all three.
Exactly. So in principle, those are all there. Those are all big things that in the thoughts of the CIO, they're worried about this stuff. Yes. Anything ourselves and NVIDIA to do to really package up repeated solutions that have been proven in the field and simplify that whole thing is, of course, very much appreciated. We kind of take the same principles in our storage. So what we do, so you can see that system in that rack, we've really squished a lot of things inside of that. And that's taken us 10 years. So you'll see some storage systems have bits of cables and stuff. We've really squished this down, but as you'll see later on, it's not compromising on performance. So I wanted to give the audience a flavor about what it is that DDN's parallel file system is doing to move the data between the containers running on the DGX, where the AI applications go, and the storage. And Pamal was mentioning one of the key things we're talking about is checkpointing, a big problem area. We always think about read, but we don't think about write. And of course, when you checkpoint data from all these systems, we're writing out from the GPUs at very, very high speed. Faster we can do it, the better. So I'm going to give you a flavor about how that data movement works.
But for people, because we mentioned it a few times, for people who aren't entirely sure exactly what checkpointing is.
Yeah, I have got a slide on it, but you're running this very large model in memory, and you're probably training it, right? And it might take, as Pramil said, it might take weeks to finish. And so there's likely that you can have some component failures, some network failures, some cables broken during that period. And so you don't have to go back 20 days to the start of the program every time that happens. So what you do is quite regularly, a few hours, let's say, you're going to take all that memory state, you're going to dump it into storage, safe and protected, so that if there is a failure, you can just restart again. There's more than one reason to do this checkpointing, but that's one of them, to protect yourself against hardware failures.
Even more storage intensive, yeah.
So let's have a look at this system, and hopefully in the next 3 minutes, people will get a really good idea about how the data is moving. So here's a DDN storage system, and here are a number of NVIDIA DGX systems. And actually, what they're doing is running containers, typically, across the GPUs. And we are also running virtualized servers and storage inside of our storage system. And what those lines are linking it are the data paths. I haven't drawn all the lines in for all the containers, just in the first system, because I was very tired of drawing lines. But what you can see here, the principle is the clients, each one of these containers, each one of these AI frameworks can talk to all the storage servers simultaneously. And this picture, I've only drawn one of our storage systems, but you know, at NVIDIA with Selene, there's like 48 of these, and we can provide a single seamless namespace, so one mount point for everything to make it super simple. So inside here, there's a couple of bits of magic happening. Firstly, the thing to note is we've got some intelligence running in the DGX. We've got some software right there. And we also optimize on the network. So we're not just a storage system. It's different from NFS-based systems, different from NAS systems. We have intelligence in the compute side right next to the applications. So this intelligent client, the main point about a parallel file system, if people sort of want to know anything about parallel file systems, they should remember this, is that the clients know where the data is and they go get it directly. And what that avoids is a big amount of inefficiency. Imagine if you didn't have that, then those clients have to go to a server, then that server has to go and do another thing and go get the data where it resides. Because our clients are installed on the DGXs, we could basically half the complexity of the system, remove backend networks, and improve performance. We also do this very fast networking. We've got a very fast networking layer, and you can imagine, it's not explicit, but from this picture, handling the networking across all these containers through multiple rails on the DGXs, through big networks to multiple storage systems in an NFS world with traditional IP addresses, that can become a bit of a nightmare. We really take all that problem away, and because we're managing the network as well, so it's very, very simple to manage those networks and very fast. Then finally, of course, the storage itself is scale out. So you have, I've just drawn one system here. We have many of those systems, but they just form one seamless namespace. So that was just a starter, Tim, before we go into a little bit more detail.
More detail, I like
basic architecture.
But for anyone who's watching this, remember you can download these slides, and so that's handy because there is a lot of detail coming up. And also, if you want to draw in the extra lines that James did,
that'll be much appreciated. Well, the end result of that is, in fact, these numbers came from NVIDIA themselves, actually run on Selene. So they executed a test against just a subset of their systems. You can see there's 12 systems in that rack, the little picture right in the middle of the graph. And that's doing 900 gigabits for reads. That's what's going to help you train your models and run your models. Mm-hmm. And then it's doing 780 gigabytes a second for writes. That's what's going to allow you to checkpoint out, do those regular checkpoints. So big reads, big writes, and a lot of both from a small amount of hardware, a small number of watts, etc. Mm-hmm. So there are details, but fortunately, we've already talked about checkpointing. So I'm going to leave this to the Friday night reading, and you can take these slides and read them yourselves. But essentially, we're pointing out, repeating that point we made. Checkpointing is a significant issue for training. I'm going to skip on to one other point, which is, during this process with NVIDIA, we've been really accepting fully that one of Jensen's morals at NVIDIA, which is accelerated computing is how to do more with less. And really, that's our kind of motto and has been at DDN for a while. How do you get more performance to applications from less hardware? And really one of the ways we do it is by full optimized stack, moving across the stack and doing optimizations outside of the storage. And I've got one tiny story about that here. This was actually a request from NVIDIA about 2 years ago. They were doing some training, and during the training process, one of the big issues is multi-epoch training. So you reread the same data set again and again and again, and you apply different parameters to your model effectively. But that means you're going to the storage all the time and moving all this data. So we implemented something called hot nodes, which allows us to basically switch a switch on the NVIDIA DGX systems and cache that data. And it really relieves the whole network and the storage from repeated accesses. Very easy to implement and gives you a huge efficiency gain. And that's, as I said, what it's all about. Now, one last thing. I was going to go through 3 things. Here's the most complicated thing. So we're talking about large language models, and these are driven by transformers. Now, everybody knows ChatGPT. There's an example there. That's the most funniest joke in the world, apparently. But these are driven by transformers, and these transformers consume a lot of memory on the compute side. And you can see what's happening here. There's a nice graph with the source in the previous slide. You can see this is a log graph, and the amount of memory they consume is going up exponentially, at least for now. So the problem becomes, how do you fit all this in memory? And the answer is you buy lots of GPUs. There's a limit to that because, GPU memory is increasing, but the model size is increasing a lot.
Yeah.
So we've tried to tackle this. And one way you can tackle it, before I move to the next slide, is you can try to basically use the memory you've got, and you're trying to fit this big model, big billion parameter model into memory on a number of GPUs. But if it doesn't fit, what you can do is you can just stream it through the memory from storage, which becomes very data intensive, but you're not holding the whole model in memory all the time. You're holding the bits you need at that time, and then you're pulling more of the model through as you need it through the production process.
It's asking a lot of your storage.
It is asking a lot of the storage, but fortunately, our storage is extremely fast. And this one kind of shows, actually, this slide shows the results.
Yeah.
I wasn't going to do a big PhD thesis on it, but essentially you're seeing a red line and a green line in those graphs. And effectively what we're seeing there is the speed we can get data into memory from our external parallel storage system versus the speed you can get into the system just from the local storage right there at the DGX. So we can exceed it because the networking that NVIDIA provides is very, very powerful, and we consume that very efficiently. So we can really drive an awful lot of bandwidth into these DGX systems. In fact, over 150 gigabytes a second, if people are familiar with the numbers. So we can really drive huge amounts of data into memory to keep these models effectively functioning and consuming CPU without becoming bottlenecked on memory.
Right.
So anyway, that was three little flavors of things which we've been doing with NVIDIA and working, and that's basically the role of storage and how it works. I'm not going to consume much more of the time, but I want to do 2 or 3 more slides concluding really the systems to give people just a fixed idea about what it is we do. So here you see what was called an AI400X2. This is what we've been shipping to all these SuperPODs over the past 2 years since we upgraded to this latest model. These numbers are huge. If you go away and compare these numbers to typically things using NFS, then you'll see they're much smaller and the systems are much bigger. So typically it's a 10x ratio between what we do with our parallel file systems and more conventional storage systems. So lots of IOPS, lots of throughput, lots of capacity in a 2U. But what people have been doing has been asking for more. So all these efficiency optimizations I've been talking about, what people want is more of this flash, more of this low latency stuff, because low latency is very important for running these models and for keeping these GPUs fed, et cetera, et cetera.
And all of yours is built on a QLC, yeah?
All of these so far have been built on TLC, unless it's,
Yes.
the audience's benefit, the more expensive, slightly faster, let's say 3-level cell flash. QLC is the next generation, but now becoming very mature. And we've just worked on this system for the last year or so to take QLC and make it performant, which has not been seen before in the market.
Well, yes.
If you remember back to that sort of data path picture I showed at the start, that's kind of the essence of why we've made QLC fast. We're not bottlenecking through any strange things or treating QLC too differently from how it wants to be treated. But the result is we now have new systems which really bring down the cost of all flash quite dramatically and allow you to expand these controllers with much more flash to give you a large capacity. And as I say, these models are getting large, the images you're training on are getting very large. And this is really a new release. We launched this at ISC, but many people in the call might not know about it. But these are, very high density, very fast QLC-based storage systems. And you can see now it's got, let's say, 6 times the number of flash devices in it that we had before with a single unit, and also they're larger. So this is an 8 petabyte system right there in that picture. And the same ones can be used to support these SuperPOD infrastructures, basically effectively lowering the cost of all flash deployments.
Yep.
Oh, so I'll conclude there. I'll conclude with this slide. This slide is a little kind of summary slide about the various integration points we've had with NVIDIA over the years around GPU Direct and around integrating with the networking and stuff. But really the point is that I've been trying to make is there's an architectural piece which makes us efficient, and there's the full stack integration piece which makes us efficient. And it's all tied into the problems that NVIDIA is seeing whilst running genuine large-scale models.
Yeah. I think one of the things that we see a lot from our customers is, depending on the work that they're doing, not only just looking at large language models, but if they're looking at multi-model, as they call it now, where they're looking at different aspects and trying to mix computer vision with language processing, and depending upon the size of the images that they are working with, especially in the biopharma side, that can become really large. So what we do is we set a baseline with our SuperPOD, and then that customers expand how much storage that they need depending upon the workloads that they're going to be training on these kind of large clusters, right? And that's the flexibility that we get working with customers, trying to figure out how they're going to scale up what amount of storage that they need with this particular, any kind of particular deployment.
I want to ask both of you, because one of the stories we keep hearing is the shortage of supply of expertise in how to build these kind of architectures to get this capability. And the clock's ticking. So a lot of organizations are having to build this fairly quickly. I would imagine there is potential to make some huge errors, some career-ending bad decisions on this. What would that be? How do we avoid doing that sort of thing when we're creating this capability, James?
Well, firstly, fortunately, the ecosystem, the software ecosystem has moved on an awful lot from what it was a few years ago. It's dramatically simpler to do. So we trained a model ourselves. We essentially took an open source kind of equivalent of ChatGPT. We trained our own documentation using the H100 system we have in our labs. And in fact, those graphs I showed you were part of that program. So as a company, really without AI framework running expertise, we were able to do that within a few weeks and get our own model trained to answer our support staff's questions on our own documentation. So much, much simpler than it used to be. But when you go to scale, then of course, everything is difficult. And that's really the problem we're trying to solve, is trying to make sure when you essentially are spending that amount of investment, not only on the infrastructure, but on the data scientists, the data, etc., that we give you the lowest risk, highest efficiency solution from end to end. And that's really what this is all about.
Yeah. Primal, what do you think about how the best ways to go about this? Yeah,
I agree. And what we're trying to do is we are trying to democratize AI. If you hear Jensen talk about it, and you hear a lot of NVIDIAns talk about it, is we're just trying to make it easier for everybody to consume and start off from a much easier place rather than have to struggle through this, right? We've gone through that struggle, we've documented it, and we made it available through reference architectures. We have the software and the frameworks already available, so they can start with that. And then, as James said, they can go and play with some of these things on the reference architectures with that hardware, rather than having to figure out what that hardware that they want to invest in. So they have a starting point, and from there they can move either left or right, depending upon whether they want to build their own hardware or continue to invest in, hey, this is where I'm going to spend my time, meaning on the workload itself rather than on the infrastructure, right? So we're trying to make it more and more easier. All our reference architectures, whether it's looking at smaller clusters like BasePod or like SuperPOD at scale, you can think of it as before it was in the HPC world, where you had a lot of time and effort you can put in to create these large clusters. But now we are making it much more easier, because we know this is tried and tested, and you can easily deploy this and get the same kind of performance that we can get on these platforms in-house, and that's available to everybody.
Well, for everyone that's embarking on this, good luck. There's a lot of work to be done, but it's work that's got to be done now. And so it's great to talk to both of you, James and Primal. It's great to talk to you because you're right at the cutting edge of this, and also because of the effort that you're putting into making this achievable, this pretty daunting prospect that we have, making it something that's realistic. Thank you very much to both of you. Thank you, James.
Thank you.
And Primal, thank you as well.
Thank you. Thank you.
Thanks to all of you for watching. Do you want some more of this? I bet you do, in which case let us know what you do when we'll put it on. It's not going to be the last time we're talking about this in the next few years. So thank you also to everyone behind the scenes at the Register who helped put this one on. We will see you soon, but until then, from me, Tim Phillips at the Register, goodbye.